Hello, and welcome to AI for Mechanical Engineering. In today's lecture, we'll be learning about convolutional neural networks, also known as CNNs. Now, CNNs are considered to be one of the most representative models, especially in deep learning, and have been considered to be a foundational model, especially in computer vision and AI-powered applications. So before we learn about what a CNN is, let's take a look at what the meaning of convolution is. So convolution by definition refers to the integral or sum of the product of two signals after one is reversed and shifted. So if we mathematically represent this, starting from minus infinity to infinity, assuming we have two signals, x of m and h of m, we flip or reverse one signal and take the sum of the element-wise product of both signals. Now if we visually represent this, first, let's assume that we have our two signals, x of n and h of n. And looking at the cross-correlation case first, in this case, we're not reversing the second signal, h of n, but rather using its original version. So again, we're taking the sum of the element-wise product, and this signal represents the output, or the cross-correlation. Now for the convolution case, we're flipping or reversing the second signal h of n, which in this case we see this flipped shape. And if we again take the sum of the element-wise product, you'll notice that we end up with a similar output yet flipped version of the original cross-correlation. Here, this result refers to the convolution. Now, both of these, from a signal standpoint, roughly show how one signal affects another. I'll be talking about this in detail later on, but for now, please keep in mind that for both convolution and cross-correlation, the key is that we're doing element-wise multiplication and summation. So if we take a closer look at 1D convolution, and one thing I'd like to clarify is that technically this is cross-correlation because we're not flipping the second signal. But for simplicity, I'll be referring to this as 1D convolution. So assuming that we're denoting our original signal as x of n and our second signal, h of n, and we'll be calling this the kernel, in which we'll be later on calling the filter. Again, the idea is that we're doing element-wise multiplication, and we're adding up all the results, or taking the summation. So if we look at this example over here, we first take the product of each element. So in the first case, we end up with 1. The second, 9. Here we have 0. And finally, minus 3. And the second step is to add up all these elements, in which we get 7. So this becomes our output. Once this is done, we shift the kernel over one time step and do the same thing. So this is being multiplied with this, and so on. And again, if we add up all these results, we end up with 9, which is shown in our second element of the output. We repeat this process up until we reach the end of the original signal. And one thing I'd like you to note here is that depending on the size of our original signal and our kernel, our output size will be different. So for instance, let's assume that our original signal length is 10 and the kernel size is 4. The output would have a length of 7 in this case, and generally speaking, we can represent the length of the output as the length of the original signal minus the size of the kernel, or the length of the kernel, plus 1. Now to implement this in Python, we can simply use NumPy's convolve function to obtain the results. So if we start off by defining our input signal as x and convolve the signal with itself, we end up with this result over here. Now, the reason why we end up with a triangular shape is because if we slide the second signal, or the filter in this case, or the kernel in this case, you'll notice that as these signals overlap, we end up with a greater value, and this can be visually represented as shown in this example. So here, can see that as both signals overlap, the result of the convolution represents a triangular shape, especially in this continuous domain. Now the question is, why do we want to learn this and where can we use this? One example can be seen in the denoising case, where we use a moving average filter. So for those of you who aren't familiar with what a moving average filter is, we're simply taking the average of the previous M data. And by doing so, we're able to obtain a smooth version of the original signal. And this can be seen as doing a convolution operation between a portion of the original signal with a kernel that has a length of M. So again, we're doing a convolution operation with a filter that looks like this. And if we graphically represent this filter, this becomes 1 over M, and we have M elements in total. And this, in fact, can be seen as a low-pass filter, especially in the time domain. And although you don't have to know what the meaning of a low-pass filter is for now, I'd like you to keep in mind that these convolution operations can be used to either modify the original signal or extract certain meanings from the original signal. So if we look at an example where we can modify the original signal, let's assume that we have our original piecewise smooth signal over here, and our kernel or filter over here. And here the kernel is defined as the following, where M is equal to 5. Now if we assume that our original signal is corrupted with some noise, our goal is to smoothen this signal using our filter over here. And just like we did for the moving average case, if we convolute this noisy signal with our kernel, we end up with a smoothened version of the corrupted signal. So this shows an example of how we can modify the original signal, and in particular we've seen an example of denoising. The second example shows a case where we can extract certain meanings or certain features from a given signal. Now, let's assume that we have the same original and corrupted signals. In this case, our goal is to identify abrupt changes in the signal, which is also known as edge detection. And this time we'll be using a kernel that looks slightly different. So if we write this out, we have minus 1 over 2 and 1 over 2. Before we take a look at what the actual results are, let's consider a couple examples. So first of all, let's look at a case where two adjacent values have similar values. So assuming x of n is 10 and x of n minus 1 is equal to 10. If we convolve this portion of the signal with the kernel, we end up with 10 times minus 1 over 2 plus 10 times 1 over 2, which is equal to 0. So this implies that any two adjacent values that have similar values will have a value that is close to 0. And as a matter of fact, this can be seen in the convoluted output results, where most of the elements have a value that is close to 0. Next, if we consider a case where two adjacent values have greatly different values, for example, x of n is equal to minus 10, and this is equal to 10, the convolved output will have a value of 5 plus 5, which is equal to 10. Implying that for an abrupt change in the signal, we are able to detect these through this particular kernel. So this, as a matter of fact, shows up as an edge or an abrupt change in the original or corrupted signal. And this is an example of how convolution can be used to extract certain meanings or features from the original signal. Before we move on to 2D convolution, let's take a look at an actual or real-world example of how convolution can be used. So here we'll be using data from an actual sensor, in particular from an IMU, which basically measures the acceleration in certain axes. In the first case, we'll be looking at the denoising example, where the goal is to smoothen the original signal. And again, we were able to obtain these results by using a moving average filter or convoluting the original signal by using a kernel with the following shape. Now, because we're using an actual sensor, you can see that the raw results obtained from the sensors are relatively noisy. And however, if we apply the convolutional operation with this kernel, you can see that we have a much more smoother output signal, showing that convolution can be used to denoise these signals. The second example is edge detection, where the goal was to identify abrupt or sharp changes in the original signal. So in this case, assuming we have the same measurements from this sensor, our goal is to identify these sharp changes that occur in the signal. And this is done by selecting an appropriate kernel that, in the previous example, had a shape that looked something like this. So these examples show how convolution can be used, especially in 1D signals, to either identify certain patterns or meanings or features from signals, or even modify these signals, such as denoising. Moving on to 2D convolution. The reason why we want to learn how to do 2D convolution is because we are mainly dealing with images with CNNs. So before I actually talk about 2D convolution, let's take a quick look at what images are. Now, images to humans look something like this, where we typically see a spatial distribution of certain hues or colors. Now, each of these colors, hues, or intensity values at each pixel location can be represented with a number. And in case of an 8-bit encoding, we have values that range in between 0 to 255. So this implies that a computer simply interprets an image as a matrix with a bunch of numbers. And although this example is shown in a grayscale, a typical image will have colors, implying that, for example, if we have a 1080 by 1080 image, and assuming that we have 3 channels, or 3 colors in this case, the computer will interpret that particular image as a 3-dimensional matrix for an RGB image. So again, a color image will contain certain values of red, green, and blue channels, and each channel can be separately represented as matrices. So a color image will be represented in 3 channels in total. And in other words, we have 3 separate matrices to represent this image. On the other hand, a grayscale image will only have 1 channel or a single matrix to represent the image. So with the concept that an image can be represented as matrices in mind, we'll be taking a look at 2D convolution. So based on the examples that we've seen so far, a convolution on an image is equivalent to doing a convolution in 2D. And just like we've done for the 1D case, we're doing an element-wise multiplication and taking the summation of that value. So assuming we have a kernel with a certain shape, if we convolve it with the original image, we're simply taking the sum of each element-wise product. And once we obtain the output, we shift the kernel over to the side and repeat it until we cover the entire image. So because we have an additional dimension in a 2D case, if we have a filter starting at the upper left corner, we convolve it in this manner, where we shift the kernel to the right and bring it down until we reach the end of the image. And if we look at an animation of this, you can see that the filter is moving from left to right, shifted down 1 pixel, and repeat it up until it reaches the end of the image. Now, just like we've seen in the 1D case, these filters, depending on how they're chosen, we can either emphasize certain features of the image or even remove certain features. And examples of this filtering include smoothing, sharpening, and even edge enhancement. So if we take a look at a slightly larger case, let's assume that we have a kernel with the following values And we start off with the upper left corner. So first we start off by this element multiplied by this over here. Repeat it for all of these elements, and then add them up to obtain our output. Now the convolved result will be shown in our destination pixel over here. And one thing you'll probably notice here is that if we finish the convolution operation, you can see that we end up with an image that has a slightly smaller size, which was also seen in the 1D convolution case, where the convolved output was slightly shorter than the original signal. Now if we look at actual examples of convolution on an image, here we'll be revisiting the concept of edge detection, especially in a two-dimensional space. The edge detection kernel in a 1D space looked something like this. In a 2D space, we're expanding it like this. And here you can see that we're effectively stacking these 1D kernels in the vertical direction, which allows us to identify abrupt changes or edges within the image. And because we're stacking these kernels in a vertical manner, we're detecting the vertical edge here. The second example is similar, but in this case we're stacking these kernels horizontally, which implies we're looking at the horizontal edges. And if we look at the results, the first case you can see that we've detected these vertical features or edges from the image. Now in the second example, we've identified the horizontal edges within the image, or patterns. And because we've used a different kernel in the second case, you can see that we're not able to identify any edges in the left corner of the image. We can also implement the denoising example in 2D. So in the 1D case, the denoising or moving average filter had the following form. And just like we've done for the edge detection case, if we expand this in 2D, we have a filter that looks like this. Now to implement the convolution operation in Python, we simply have to use the convolve2d operation. And once we define our kernel over here as m, we convolve our original image with the defined kernel. And as a result, we obtain a smooth image, just like we've seen in the 1D case. And the final example is blurring, where the goal is to apply a convolutional filter that has this Gaussian kernel. So if we look at this filter or kernel from the side, we have this two-dimensional bell curve. And if we convolve this original image with this particular filter, we have a blurred version of the original image, as shown here. So based on all of these examples, we've been able to see that depending on the choice of kernels, we are able to either extract certain features or remove certain features from the image, or even modify the original signal. And from a conventional image processing standpoint, the goal is to find the right kernel. So people have been effectively trying to design certain kernels that have specific effects on the images. However, for CNNs, we'll be using an opposite approach. So instead of handcrafting these kernels for certain purposes, we're learning the optimal or the best kernel that is suitable for the given task from data. So this is one of the reasons why CNNs have been such powerful tools, especially in machine learning. And we'll be learning how these data-driven kernels can act as certain feature extractors, especially when using a deep learning framework. Now, this is the main foundation of CNNs. So in today's lecture, we've learned what a convolution is and looked at some examples both in 1D and 2D. We've also learned that through convolution, we're able to either identify certain features from the image and modify the original image or signal. This is the end of today's lecture, and thank you.